terms of things that we can't predict.
Yeah, but the thing is, all the smartest men in the world, like, the thing is, they were just talking about Einstein a lot, and they were talking about this postulate and how they were so worried about attributing things to the, like, quantum behavior, because that's, like, the catch-all for, like, I can't explain it, but we can observe it. Like, our math and intelligence isn't there. And it was talking about how, like, Einstein was shook and all these guys were mentally in a pretzel about, like, they're worried about, like, attributing things to quantum behavior, because then 20 years later their friends would be like, no, we can explain it with this classical physics thing. And they're like, you're a fucking idiot. So the fact that Einstein probably had that go through his head, and he's the smartest human of the 19th century that's famous, funny. That's what I call good humor. That Einstein was mentally in a pretzel because of this.
Fuck. I gotta remember the question. So we've been smoking for basically the entire day, so short-term memory.
You've been smoking the entire day.
Oh wait, no. Let me go. Quick question again. What was the second one? Was like, what's the implications of quantum physics for like us understanding certainty?
Yeah, or honestly for answering questions that we haven't been able to answer so far.
I'll answer that one because the first one's just the prelude to all of quantum like mechanics, and I don't really want to go from like the ground. So this is gonna assume you have like all breakdown bites, but like the implications are how with quantum mechanics and how it leads to quantum computing, with like how traditional computers or classical computers are, it's either a 1 or a 0, like it's a bit of information. It's like recorded by, in its simplest form, like an electron going, either it's an on or off state, and so that builds everything for like digital technology and like us being able to use computers, like processors, CPUs. It's just like, yeah, I mean, I can go over Moore's law later if you want for a later video, but like the amount of like integrated circuits, or the amount of transistors they can fit into an integrated circuit doubles every 18 months. So like, and it's been done that every year for like a long time. And there's like thoughts on if it'll slow down and how like other stuff with like, there's a lot of like current implications, but it hasn't been disproven. So literally computers are getting really fucking crazy on a crazy scale. And even in the last like 20 years or 10 years, because of just Moore's law and how like fucking much they can just fit into a small same surface area. And so imagine how crazy that is that that's recording 1 electron. And so we can do a lot. So a lot of passwords, its simplest way to explain it is through like cryptography of like, literally it's computers can do some things very well, but some things not well during the confines of literally math and physics, because it's at its simplest, remember, it's literally just 1 electron, either on a elevated or a 0 state. It's 1 or a 0. So it all goes back to that at its simplest.
So it's like the underlying code of the universe.
It is, but no, I'm describing a classical computer versus a quantum computer, and that'll give you the reference. And I don't have the stats on me, but like the way it was described to me in the book I read, it gives a crazy like relative contextual comparison with like grains of sand and like Mount Everest and like some crazy like scale dimensions, similar to like when you look at like our speck of Earth in the context when they zoom out. Like so classical computing, it's 1 or 0. Quantum computing leverages like different phenomenon with quantum particles, which is just the smallest unit of anything, like a quantum particle. And like the two big ones are quantum entanglement and quantum superposition or superposition. I get confused on like saying it out loud because I don't talk about it that much, but like I read the word a bunch. But quantum superposition is basically the idea that it, instead of being a 1 or a 0, it exists as both a 1 and a 0 at the exact same time. And that's where like the Schrodinger's cat comes. The classical example of like, if you have a cat in a box and it's honestly, I learned it when I was a lot younger and they didn't tell me like the actual like math part of it. So like the simple, I'll tell you both versions. The one version is you have a cat in a box and it's basically the cat, you have something in the box that kills it, and you don't know if the cat is alive or dead. So in theory, it's alive and dead. And when you open the box and you observe it, because observation is a very important thing in physics, because quantum particles act different when they're observed versus not observed. The cat dies. You are forcing the reality of the cat to either be dead or not dead, because in its state, when you don't observe it, it's both alive and dead because of the radioactive material. That's the second part I learned recently, but it's because of like the radioactive decay is a lot of like, that's one of the big things in quantum, like just the quantum field is like radioactive decay is, you can do a lot with it just because it leverages like quantum behavior in a crazy way. But, and I don't want to go over that, but in the simplest, the last thing I'll say, and then we can go, is you're forcing reality to happen onto it, and so that's quantum. So you're forcing reality. So the quantum bit isn't a 1 or a 0. It's literally both at the same time. So the exponent, it's 2 to the 3. So every bit exists. So in traditional computing, like the exponential scale is like when you have 3 bits and like electrons, it's a 1, 0, 1. When you have 3 qubits, so it's a bit versus a qubit, is what the exponential answer is, how you get certainty, because it's just the processing power, like the actual like physics of like how they leverage like their spin. There's a lot of actual like physics that like, not for this video, but like, no, they're leveraging the hard stuff. So a qubit, and it's the crazy thing I'll tell you after is that it's not just in traditional computing, it's how many transistors you have, and like more is always better. You just like, that's how you get more power. In quantum mechanics, it's always good to have more qubits, but like different, like Google's quantum computer, IBM's, they all leverage different types of properties. So if you have less qubits, but you like leverage certain properties like spin of like the actual like quantum physics, you can have a better supercomputer, because the scale of how much a qubit is, I think you get 3 permutations, or no, you get 8 permutations from 3 qubits versus 3 bits is 3 bits. So like the exponent scale, I think, is 2 to the 3. So it's 2 times 2 times 2. So 2 to the 8. Or so it's just, no, it's 8. So it's like, that's the ratio. So imagine if you have a quantum computer and it tells you like when they started, like it's a recent history in like the early thousands is when they really started to be like efficable. But we're building more. So the answer to that question is we can do a lot of really intense math with classical computers. But quantum computers are so much fucking crazier because they leverage all these properties that we don't know exist, but we leverage them to just do like crazy mathematical functions. So a lot of quantum computing, when it becomes at a high scale and they do very specialized tasks very well, but they're not like AI, it's not like ubiquitous. It's like they can do this one math problem fucking crazy. But the thing is, cryptography is all based on, a lot of it's on like, it's prime factorization mostly. So it's like, no, it's a one-way math function. So you can take 2 prime numbers and multiply them. This is the last thing and we're gone. This is literally the 2 different, this is a good explanation of like quantum versus traditional computing. If it makes sense, I have no fucking idea because I'm so high right now and we need to go to a sauna. Fuck, it's 5:01. We're going to finish this later because our ride leaves in a minute prior. We got to go. End of the video.
That was great.
Holy shit.
More to come on quantum physics.
Yeah.